Oops. Okay, so in this video we're going to talk about Swartz reaction and the Halide exchange. Okay, so I'm going to start off with the Halide exchange first. So the Halide exchange is a reaction used to prepare iodides. Okay, generally it's historically used to prepare iodides. Now the reaction goes like this: if you have say an Rx where X is not equal to fluorine or iodine, so basically bromine or chlorine. Okay, so you react it with sodium iodide in the presence of acetone. Okay, you guys know CH3, CO, CH3, right? You get Ri plus NaX. Now this is basically it. You want to know one more thing, that see NaX where X is bromine or iodine, Br / bromine chlorine is less soluble compared to NaI. So in that way you can see how this reaction works, because it's heading towards more stability, right? You're forming a more, like the less soluble you are, the more solid like you are, right? The more solid like you are, the more the lesser entropy you have. So it's gonna you're gonna become more stable that way. So you're gonna move in this direction. First of all, I think you guys are jumping right now saying, don't all processes move towards greater entropy, and that, yeah, that's true. But I'm just talking about stability. Okay, generally, if you are precipitating, right, it's considered like if you will form something which will precipitate, you generally move towards that direction. Okay, it's just some intuition you get from looking at reactions, that if you are going to form a less soluble substance, you generally try to move towards that direction. Okay, I just gave you an example of entropy to show that it's much more stable that way. Because see, a solid is much more stable than a liquid, right? There's not going to be much change in a solid. That's think of it that way instead of thinking of the entropy argument. Okay, so that's something you want to keep in mind. Another thing you want to keep in mind is that, remember I told you in the starting videos that I looked at the order of nucleophilicity, right? Who is a stronger nucleophile? Br minus. And I said that since Hi is the strongest acid, I minus is the weakest conjugate base. Weakest base means weakest nucleophile, so base strength, nucleophile strength increases this way, right? But then you should ask me, then how is iodine able to replace bromine or chlorine? And that will be a very valid question you have. And the answer to that question is that this was only for polar solids, polar protic solids. Protic solids means any solvent which has an acidic hydrogen. In fact, even water is considered to be a polar protic solid. Water, methanol, these guys are a good old neighborhood friendly protic solids. Okay, and so see, the argument that Hi is the strongest acid can only take place in water, right, or ethanol or something like that. You cannot argue that water is the strongest acid if there's nowhere to give the Hi is the strongest acid, there's nowhere to give the H plus, right? So you argue it this way in a protic solvent. In an aprotic solvent, it's actually the opposite. Aprotic solvent means any solvent which does not have an acidic hydrogen, an example of which is acetone. You also have many, you have DMSO, dimethyl sulfoxide, DMF, dimethyl formamide, HMPA, hexamethyl phosphoric acid. All these guys are aprotic solvents, okay, and these are actually very strong aprotic solvents. But even acetone is an aprotic solvent, and in aprotic solvents, the nucleophile strength reverses order. Okay, once again, why is that true? Is kind of out of your scope of syllabus right now, so no need to go on that. I will maybe add that in the final video where I'm talking about iodine also. But for now, you can understand that, because in the previous video only I told you that only a stronger nucleophile can replace a weaker nucleophile, right? It's like that displacement reactions you guys learned. So that's why. So this order actually shifts when you go from protic to aprotic. Okay, that's something you want to keep in mind. So that is basically the two things you want to remember for Halide exchange. Remember the acetone, don't forget the acetone. NaI acetone is just a famous combination. Okay, and the final method of preparation of haloalkanes is Swartz reaction. Basically used to prepare fluorides. Basically, what you do, you take Rx, silver fluoride, you give Rf plus AgX. Super simple reaction. Happens in product solvents. Why? Because fluorine should be a stronger nucleophile than X minus, right? Which means it should happen in a product solvent. So even water itself is generally enough for this reaction. Okay, so Swartz, if you see ever see a fluoride in something, in some conversion, the last step is going to be Swartz reaction. So AgF isn't necessary. You can use in your loop test some other list of substrates used, antimony difluoride or something that's used. So you can use that also, but generally AgF is used. Okay, so that actually concludes methods of preparation of haloalkanes. Okay, and before we the next topic in chronological order is actually physical properties of haloalkanes and then chemical properties of haloalkanes. But since your guys are in the organic chemistry mood, hopefully by now, we will jump into preparation of haloarenes first, where we will invoke some of our 11th grade chemistry once again. Finish up with that, and then we'll move on to discussing properties and stuff. Okay, so take care, guys. See you in the next one.